Welcome to the webinar. The intention here is to, at a fairly high level, give you some concepts that can be used to optimize the design of liquid-filled transformers. Brad, if you can go to the next slide, please. So insulation material, so optimize ingredients for solid transformer insulation. Next slide, Brad, please. So when we're looking at the insulating material itself, it has some fairly high performance requirements. From a dielectric standpoint, it has to have high breakdown voltage and low dissipation factor. Power factor is another term used for this. From a mechanical standpoint, it has to be very strong. So we'll talk later about one of the criteria, which is short circuit strength. But the material has to have high tensile strength, high flexure strength, also known as beam strength, and then low compressibility. And then from a thermal standpoint, we need to have a high thermal class and a high degree of polymerization, which is the length of the cellulose molecule as the board or paper starts off. The challenge for the board maker or the paper maker is all of these performance criteria can only be achieved using two raw materials, basically water and cellulose pulp. So particularly the strength and the dielectrics, we have to be very careful about those raw materials. Next slide, please. So from the cellulose standpoint, there's two important criteria. First of all, the wood that's used from the trees should be from softwood trees. These are longer fibers and actually wider fibers that give us our mechanical strength. And they're also typically sourced, at least for Weidmann products, from what's called boreal forests. And I put this map here in the upper left of the boreal. These are old growth forests, typically or in the northern climates. And because these trees grow so slow, we end up getting very, very strong fibers for that. Again, we can't put any strength additives in our material, so it's really important to start with good fiber. It's important to note that these are coming from sustainable forests. There's the pulp suppliers that we deal with are part of this Forest Stewardship Council, and in order to be certified, you have to plant 2 trees for every tree that you harvest, so it maintains a sustainable forest. The other point to get a good, pure, strong fiber is when you derive the cellulose from the tree itself, there's a process called pulping, which can get those fibers out. And there's a pulping process called the Kraft or sulfate process, and this is the best process. It's the most gentle on the fibers, and again maintains this long length. So 2 criteria: softwood trees from boreal forests, and then the cellulose fibers are derived using the Kraft process. Next slide, please. The second point, the second raw material, so we talked about cellulose fibers from the Kraft process, and the only other ingredient is water. So in order to make a good dielectric material, we need to have water with low conductivity, low chlorides, neutral pH. So if you have an electrical grade board or paper plant, then it should be sourced near a good water supply. If you look in the upper right, that's our press board mill in Rapperswil, Switzerland. The lake you see there in the background is actually the Lake of Zurich. So this is very clean water that we use for our processed water. The lower one, this is where Brad and Jason and I are from, St. Johnsbury, Vermont, and that's a pond that we get our water from for the facility as well. Okay, next please, Brad. Okay, so the next concept is that we want to optimize the space factor in the winding. So the windings for large power transformers are going to be insulated with a craft paper. When you're doing the design of the winding, you know what the turn-to-turn stresses are. So you want to be able to withstand those stresses, and that's determined by the thickness of the paper and the number of layers. Once that's determined, the space factor of your winding is going to be improved tremendously by how tightly you can wrap these papers onto the conductor itself, which you can see in this photo here. So this tightness of the paper is largely determined by the strength of the paper. So tensile strength is how much force it takes to pull the paper apart. And then another important criteria is elongation. So how much the paper is going to stretch before it breaks. And if you can imagine, if you have this high-speed wrapping machine, then if you had high elongation, very stretchable paper, then you're able to wrap it much more tightly. So the best conductor insulation will have both high tensile so it doesn't break, and then high elongation so it stretches and it can be wrapped very tightly. Next slide, please. So how do we achieve that? One of the processes that actually Weidmann acquired from a company called Denison is a process called calendaring and creping. So the first process is creping. So if you look in the upper right, that's taking a paper and putting it through a process that gives these folds. If you think of, say, Halloween decorations, you have crepe paper that you use as a decoration. It's very stretchable. However, if this was your end result, if you look at the upper right, then you can imagine that the thickness tolerance of this paper would be very broad. So the second process that's used once it's creped is it goes through a calendaring process. This lower right photo is a close-up of a calendar with a paper product going through the calendar. So it's two steel rolls that come to a nip location, and that densifies the paper, and it also gives you a very uniform thickness. So by doing this first calendaring, which increases the elongation, and then first creping to increase elongation, and then calendaring, you end up with getting the thickness tolerance of a normal flat non-crepe paper, but with the strength and elongation of a paper. And by using that paper, you can definitely increase the space factor in your